Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about characteristics of the system response. And what is system response? When x of t is a random signal, that signal x of t is applied to a LTI system, linear time invariant system, whose system response is y of t, and its system response y of t is given by convolutional integral, and it is given by y of t is equal x of t convolution h of t, which is equal integral minus infinity to infinity x of tau into h of t minus tau d tau. But the convolution operation satisfies the commutative law, that is x of t convolution h of t is equal h of t convolution x of t. So using this convolution h of t convolution x of t, the convolutional integral expression is integral minus infinity to infinity h of tau x of t minus tau d tau. So this is the definition of the system response and the convolutional integral. Okay. First we are going to discuss about mean value of the system response y of t. And what is the mean value of the system response? If x of t is a random signal, that the random signal x of t is applied to linear time invariant system, then the output of the system or the system response is y of t. And the system response y of t is always convolution of the input signal x of t with impulse response h of t. So using convolutional integral, the system response y of t is integral minus infinity to infinity h of tau x of t minus tau d tau. So now here x of t is the random signal, that is the input to the system. So in this equation, take the expected value on both sides. Taking expectation on both sides, we get expectation of LHS term is equal to expectation of RHS term. So that is expectation of y of t is equal. So now here on RHS side, applying the expectation into input to the signal. And what is the input to the signal? That is random signal, that is x of t. So x of t minus tau is the shifted input signal, applying the expectation to the random signal. So therefore, the RHS term is expectation of y of t is equal integral minus infinity to infinity h of tau into expectation of x of t minus tau d tau. Since the random process x of t is a wide sense stationary random process, its mean is a constant value. So that is expectation of x of t minus tau is equal to expectation of x of t. X of t is a stationary random process. The condition of the stationary random process is a constant value. So that is expectation of x of t minus tau is equal to expectation of x of t. So this expectation of x of t is also denoted as m suffix x or x bar. So therefore, applying this condition into RHS side of the above expression, we get expectation of y of t is equal. So expectation of x of t minus tau is the x bar or mx, x bar into integral minus infinity to infinity h of tau d tau. So we know that for a linear time invariant system, its impulse response and transfer function form a Fourier transform pair. So that is Fourier transform of h of t is equal to h of omega. So the definition of the Fourier transform of the impulse response is h of omega is equal integral minus infinity to infinity h of tau into e power minus j omega tau d tau. So now here substitute omega is equal to 0, we get h of 0 is equal e power minus 0 is 1. So therefore h of 0 is equal integral minus infinity to infinity h of tau d tau. So this equation is called as zero frequency response of the system. So now here in this equation on RHS side, integral minus infinity to infinity h of tau d tau is the zero frequency response of the system. So applying this condition into this equation, we get the mean value of the system response is expectation of y of t is equal x bar into h of 0, x bar into h of 0. So in this equation, it is noted that from this equation we can observe that the mean value of the system response is equal to the mean value of the random process x of t times area under the impulse response if x of t is a Whitson stationary random process. So that is expectation of y of t is equal expectation of x of t into h of 0. So this is the concept of the mean of the output y of t. And next we are going to discuss about mean square value of the system response y of t. So the mean square value of y of t is expectation of y square of t. So y square of t is written as y of t into y of t, but y of t is the output of the system response, and the system response y of t is the convolutional integral, that is y of t is equal integral minus infinity to infinity h of tau into x of t minus tau d tau. So now here the first y of t is written as using convolutional integral minus infinity to infinity h of tau 1 into x of t minus tau 1 d tau 1. Similarly, second y of t is also written as using convolutional integral minus infinity to infinity h of tau 2 x of t minus tau 2 d tau 2. So applying the expectation only the random signal, so that is RHS term is integral minus infinity to infinity integral minus infinity to infinity expectation of x of t minus tau 1 into x of t minus tau 2 into h of tau 1 into h of tau 2 d tau 1 into d tau 2. If the input signal is a Whitson stationary random process, then Rxx of t1 comma t2 is equal expectation of x of t1 into x of t2. Rxx of tau 1 minus tau 2 is equal expectation of x of t minus tau 1 into x of t minus tau 2. So now here in this equation on RHS side, expectation of x of t minus tau 1 into x of t minus tau 2 using the definition of the autocorrelation function of the random process, that is written as Rxx of tau 1 minus tau 2. Rxx of tau 1 minus tau 2. So therefore expectation of y square of t, that is mean square value of the output y of t, is integral minus infinity to infinity integral minus infinity to infinity Rxx of tau 1 minus tau 2 into h of tau 1 into h of tau 2 d tau 1 into d tau 2. So this is the expression of mean square value of the output y of t. So this equation indicates that use the power in y of t, but it is tedious to calculate this power in most of the cases. So this is the concept of mean square value of the random process and mean value of the output y of t, mean value of the output y of t and mean square value of the output y of t.